Welcome back, everybody, for another deep dive. This time we're going to be tackling a topic that I think is both fascinating and a little bit terrifying, and that is the end of the universe.
Ooh, exciting.
We've got a great article here just called straight up The End of the Universe, and an academic paper on black dwarf supernovae. So,
wow.
Ready to kind of explore the ultimate fate of everything.
I am. Let's do it. This will be a journey that takes us to the very limits of our understanding of physics and cosmology, I think.
Well, let's start with what we know, I guess. Our universe is expanding, galaxies are moving apart, stars are constantly being born and dying.
Right.
But what happens when all the stars burn out? What's like the next chapter in this cosmic story?
Yeah, well, you've probably heard about the universe eventually reaching a state called heat death.
Uh-huh.
Not a very cheerful name, but it essentially describes a universe where everything is at the same temperature and there's no more energy available to do any work.
So like a cosmic engine running out of steam.
Exactly. And it all comes down to the concept of entropy.
Right.
Which is, the tendency for things to become more disordered over time. The universe is constantly moving towards a state of maximum entropy where everything is spread out and evenly distributed.
Okay, so everything gets spread out, reaches the same temperature. What happens to the stuff in the universe?
Yeah.
The stars, the galaxies, all the matter.
Well, one of the most mind-bending ideas is that all matter over these vast stretches of time could eventually convert into iron.
All right.
You see, iron is the most stable element in terms of nuclear binding energy.
So even the stuff that makes up planets and stars could eventually become iron.
That's the idea. And it's driven by a process called quantum tunneling,
right,
where particles can essentially tunnel through energy barriers that would normally prevent them from interacting. It's incredibly slow, but given enough time, it could fundamentally change the composition of the universe.
So imagine a universe filled with, like, iron stars.
Yeah.
Iron planets.
Iron everything.
It's a strange thought.
Yeah, it's certainly a very different picture from the universe we see today. But there's another wrinkle to this iron paradox. Some physicists believe that protons, the building blocks of atomic nuclei, might actually decay over incredibly long timescales.
Proton decay. So even the iron might not be the final word.
Exactly. If protons decay, then the universe might eventually consist of just a sea of subatomic particles, like electrons and neutrinos, and perhaps some exotic particles we haven't even discovered yet.
Okay, so we've got this picture of a universe where everything is spread out, cold, and maybe made entirely of iron or even simpler particles. But what about the stars themselves?
Right.
We know they don't last forever. What happens when they die?
Well, it depends on the size of the star. Smaller stars like our sun will eventually swell up into red giants, then shed their outer layers, leaving behind a white dwarf, which are incredibly dense. It's about the size of the Earth, but with the mass of the sun.
And they just kind of sit there, cooling down over time.
That's right. Over trillions of years, they'll slowly radiate away their heat and eventually become black dwarfs, cold and inert remnants of their former glory.
Okay, so smaller stars become white dwarfs, then black dwarfs. What about the big guys? The massive stars.
Yeah, massive stars go out with a bang, ending their lives in spectacular supernova explosions.
Right.
These explosions scatter heavy elements into space, seeding the next generation of stars and planets.
So even in death, stars contribute to the cycle of cosmic creation.
Absolutely. But the remnants of these massive stars are also fascinating. They can leave behind incredibly dense objects called neutron stars, which are essentially giant atomic nuclei just a few miles across.
Wow, a giant atomic nucleus. And what about the most extreme remnants, the black holes?
Right. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They're the ultimate cosmic sinkholes, swallowing anything that gets too close.
So we've got black dwarfs, neutron stars, and black holes scattered throughout the universe.
Right.
But what happens to the galaxies themselves? Do they just kind of hang out forever?
No, they don't. Galaxies themselves can collide and merge, forming larger elliptical galaxies. This process actually disrupts the spiral arms that are crucial for star formation. So it leads to a gradual decline in the birth of new stars.
So even though galaxies are colliding and merging, it actually leads to a less active universe.
Precisely. And as existing stars burn out, galaxies gradually boil off over incredibly long timescales. Stars and other matter can be ejected from a galaxy due to random encounters and gravitational interactions.
So galaxies are kind of like evaporating over time. That's wild.
It is. And this evaporation process is accelerated by the expansion of the universe itself.
Right.
Driven by a mysterious force called dark energy, the universe is not only expanding, but it's expanding at an accelerating rate.
So everything is moving farther and farther apart, galaxies are spreading out, and the universe is becoming increasingly empty and cold.
Right.
It's a pretty bleak picture, to be honest.
It's getting there. Yeah.
But this is where the idea of black dwarf supernovae comes in, right?
Exactly. And this is where things get truly mind-bending. Even in the seemingly dead and empty universe, there might still be a spark of explosive energy lurking in the darkness.
Okay, I'm hooked.
Yeah.
Tell me more about these black dwarf supernovae. How can something that's essentially a cold, dead star explode?
Well, remember that process of quantum tunneling that slowly converts matter into iron?
Yeah, the one we talked about earlier.
It turns out that this process, while incredibly slow, can have dramatic consequences for black dwarfs. As a black dwarf slowly converts to iron, something very interesting happens to its internal structure.
Okay, I'm all ears. What happens?
Well, black dwarfs, despite being incredibly dense, are still supported by a force called electron degeneracy pressure.
Okay.
It's a quantum mechanical effect that prevents electrons from occupying the same state. But as the black dwarf converts to iron, the number of electrons per nucleon decreases, which weakens this pressure.
So the black dwarf is slowly losing its ability to support itself against gravity.
Exactly. And this is where the Chandrasekhar limit comes in. It's a critical mass limit for white dwarfs and black dwarfs. If a black dwarf exceeds this limit, it can no longer support itself and will collapse.
And this collapse triggers a supernova.
It's a distinct possibility. As the core collapses, it can heat up and trigger a runaway fusion reaction, releasing an enormous amount of energy in a supernova explosion.
Wow. A supernova from a dead star. That's mind-blowing.
It is. And what's even more amazing is that these black dwarf supernovae might be the last hurrah of the universe, the final fireworks show, before everything truly fades to black.
This is all so fascinating, but I have to admit, my brain is starting to feel a little overloaded. I think we need to take a break and let all of this sink in.
I agree. It's a lot to process. But we've only just scratched the surface of this incredible journey to the end of the universe.
Yeah, it is a lot to take in, isn't it? Thinking about the end of everything. But I find it strangely comforting, too, in a way.
Comforting? How so? Well, it puts things into perspective, don't you think? Our everyday worries and anxieties seem a bit insignificant, compared to the vastness of cosmic time and the inevitable fate of the universe.
You've got a point there. It's like looking up at the night sky and realizing just how small we are in the grand scheme of things.
Exactly. And that sense of perspective can be liberating. It allows us to focus on what truly matters, to appreciate the beauty and wonder of the present moment.
So even though we're talking about the end of the universe, it's not necessarily a depressing topic.
No, not at all. I think it's a deeply philosophical and even inspiring topic.
Okay.
It forces us to confront these big questions. What is the meaning of existence? What is our place in the universe? What is time? And how does it shape our understanding of reality?
Those are some heavy questions. But I think you're right. Exploring these ideas can be enriching.
Yeah.
It's like we're stretching our minds to encompass the vastness of the cosmos.
Yeah, absolutely. And in the process, we might even learn something about ourselves.
So let's continue our journey to the end of the universe. We've talked about stars dying, galaxies fading, and the possibility of black dwarf supernovae. But this end of the universe article also delves into some other fascinating and somewhat unsettling possibilities.
Yes, it does. For example, it talks about how even things like planets and black dwarfs, which seem incredibly solid and enduring, could eventually sublimate or ionize despite the incredibly low temperatures of the far future.
Sublimate, like dry ice turning directly into gas.
That's a great analogy. And it might seem counterintuitive because we usually think of ionization as something that happens at high temperatures.
Right.
When atoms are smashed apart by energetic collisions.
But in far future, the universe will be incredibly cold.
Exactly. And that's why this idea is so fascinating. The article explains that in a universe that's constantly expanding and becoming more diffuse, ionization can happen even at extremely low temperatures.
So even in a universe that's cold and empty, matter can still spread out and break down.
Precisely. It all comes down to entropy again. That tendency for things to become more disordered over time.
Right.
Even at low temperatures, the universe is still trying to reach a state of maximum entropy where everything is as spread out and disordered as possible.
The article uses a thought experiment to illustrate this point. They imagine a box of hydrogen gas that's constantly expanding,
Right.
while the temperature remains constant.
Okay.
even at very low temperatures, the hydrogen will eventually ionize just because it has more space to spread out.
It's a great example because it highlights how the expansion of the universe itself contributes to this process of spreading out and breaking down.
Okay.
Even at low temperatures, the increase in entropy from expanding into a larger volume can eventually overcome the energy cost of ionization.
So it's not just about temperature, it's also about the available space.
Exactly. And this process is further enhanced by the accelerating expansion driven by dark energy. The universe is not only getting bigger, it's getting bigger faster and faster.
Okay, so we've got matter slowly being pulled apart and ionized even at incredibly low temperatures. But the article also mentions something called the cosmological horizon, which seems to complicate things a bit.
Yes. The cosmological horizon is a fascinating concept. It's similar to the event horizon of a black hole, but on a cosmological scale.
Okay.
It's the boundary beyond which we can no longer observe any events because of the accelerating expansion of the universe.
So it's like a cosmic event horizon.
Exactly. And just like black hole horizons, cosmological horizons are thought to emit a faint thermal radiation known as Hawking radiation.
So even though the universe is expanding and cooling, there's still this background level of radiation coming from this cosmological horizon.
That's right. And this radiation actually sets a lower limit to the temperature the universe can reach.
Wait, so the universe can't reach absolute zero?
Nope. There's a theoretical minimum temperature, something like 1030 Kelvin. It's incredibly low, but it's not zero.
So even in this incredibly dilute and cold universe of the far future, there's still a tiny bit of warmth.
In a sense, yes. And this background energy is thought to be enough to eventually ionize any remaining matter, even things like neutron stars, which are incredibly dense and tightly bound.
Wow. So everything eventually gets broken down into a sparse sea of fundamental particles bathed in this incredibly faint radiation from the cosmological horizon. That's a strange and almost poetic image.
It is, and it highlights how the universe is constantly seeking balance, even in its final stages.
But even in this seemingly final state, this end of the universe article suggests there might be a twist. They mentioned something called Poincaré recurrence. What is that?
Poincaré recurrence. It's a mind-boggling concept that arises from considering the nature of eternity and the implications of a finite universe with a finite amount of energy.
Okay, you've officially piqued my curiosity. Break it down for me.
In simple terms, Poincaré recurrence suggests that in a closed system, any state that's physically possible will eventually recur given enough time.
Wait, so you're saying that even after the universe reaches this cold, dilute state, it's possible that it could somehow, like, rewind itself?
Yeah. That's the basic idea, though rewind isn't quite the right word. It's not so much a reversal of time, but a recurrence of a particular arrangement of matter and energy.
So even after the stars have died, the black holes have evaporated, and everything has reached this state of maximum entropy, it's possible that random fluctuations could eventually bring about a new beginning.
It's a highly speculative idea, and there are many assumptions and caveats involved. But it's a fascinating thought experiment that highlights the potential for truly mind-boggling events when we're dealing with timescales approaching infinity.
So even in a universe seemingly destined for heat death, there's a glimmer of hope, a possibility of renewal.
It's a possibility, however remote, and it speaks to the inherent unpredictability of the universe, the potential for surprises that defy our current understanding.
Okay, I think we need to pause here for a second and let our listeners absorb all of this. We've gone from black dwarf supernovae to the evaporation of black holes to the universe potentially restarting itself.
I agree. It's a lot to digest. But these mind-bending concepts really challenge our understanding of time, space, and the nature of reality itself.
We'll be back shortly to wrap up our exploration of the universe's ultimate fate and what it all means for us. Welcome back to our deep dive into the end of the universe.
Yes.
We've covered some pretty mind-blowing concepts so far, from the slow fade of stars to the potential for like a cosmic reset.
Right.
But what does it all mean?
That's the big question, isn't it? And I think it's one that each of us has to answer for ourselves. But I do believe that contemplating the end of the universe can offer us some valuable insights.
Like what? I have to admit, it's hard to find much comfort in the idea of everything eventually fading away.
I understand that perspective, but for me, it's about recognizing the beauty of impermanence. Everything in the universe, from stars to galaxies to our own lives, is in a constant state of flux. Nothing lasts forever.
So instead of fearing the end, we should embrace the changes that are happening all around us?
Exactly. Change is the only constant. And recognizing that can help us appreciate the present moment even more.
That's a powerful thought. It's easy to get caught up in the everyday hustle and lose sight of the bigger picture.
It is. But when we consider the vastness of cosmic time, our worries and anxieties can seem a bit insignificant. It's a reminder that we're part of something much grander than ourselves, a cosmic story that's been unfolding for billions of years.
And that story will continue long after we're gone.
Absolutely. The universe will keep evolving, changing, transforming. And while our current understanding suggests it might eventually reach a state of heat death, that doesn't mean it's the end of everything.
You mentioned earlier the possibility of Poincare recurrence, the idea that the universe could eventually restart itself.
Yes, it's a fascinating and highly speculative idea. But it highlights the fact that we don't have all the answers. There might be processes and forces at work in the universe that we don't yet understand, forces that could lead to unexpected outcomes.
So there's still a sense of mystery, of the unknown, even when we're talking about the end of the universe.
Absolutely. And I think that's what makes cosmology so captivating. It's a constant exploration, a quest to understand the deepest secrets of the universe and our place within it.
Well, I have to say, this deep dive has certainly expanded my perspective. It's made me realize that the end of the universe isn't necessarily a bleak and depressing event. It can be seen as a natural part of a grand cosmic cycle, a cycle of creation, transformation, and renewal.
I couldn't agree more. And even though we might never know for sure what the ultimate fate of the universe holds, the very act of asking these questions, of exploring these ideas, is what makes us human. It's what drives our curiosity, our thirst for knowledge, our desire to understand the world around us.
So as we wrap up this deep dive, what's one thing you'd like our listeners to take away from our exploration of the end of the universe?
I'd say this: embrace the mystery, embrace the unknown, and never stop asking questions.
Well said. Thank you for joining us on this incredible journey to the end of everything and back. We hope it's given you a new perspective on the universe and our place within it.
It's been my pleasure.
And to our listeners, until next time, keep looking up at the stars and wondering about the infinite possibilities that lie beyond.